welcome back to Symmetries and Quantum Mechanics. In the last lecture we finished with the definition of something called a class function. We're going to pick up where we left off and use the space of class functions for a group to tell us how many irreducible representations a group actually has. So here's the story so far and why we're interested in class functions and why we're interested in the irreducible representations. If you remember, the most important things in quantum mechanics, according to the point of view that I promote in this lecture, is that symmetry transformations in quantum mechanics, they are things that implement symmetries, and they should be labeled by elements of a group. So translating in time should be labeled by the elements of the real number group. Every translation in time is labeled by the time you translate for, t, which is a real number. And how do you do these things in quantum mechanics? Well, you need a corresponding unitary operator for each one of these symmetry transformations, thanks to Wigner's theorem. And so that tells us that we really should have a bunch of unitary operators, one for each element of the group, that does the symmetry transformation on some Hilbert space H, which is the one associated to our physical system. And of course, this rho has to be a homomorphism, right? Meaning that if you do nothing, you get nothing. And if you do one thing after the other, you better get the product. And then we highlighted in the previous lectures the very important role played by irreducible representations. These are the atoms of representation theory, and all representations in our part of this course, which is to do with finite groups and locally compact groups, they decompose always as a direct sum of copies of these representations. Oops, I should put it, I'll make this a K. And each one of these irreducible representations has a corresponding irreducible character. So as long as you know how to do direct sums and tensor products, then you know how to build these representations, these unitary representations here. So this is what we've so far discovered. We've even discovered how many times the representation Vk appears. Oops, that should be a J. How many times the representation Vj appears in this decomposition. You know, we've got a formula for this Mj. Mj is you take the character for the representation that you have, and you take the inner product with the representation, the irreducible representation you want to count, and that tells you how many times it appears in the decomposition. So this is, you know, an almost completely satisfactory theory, almost, because it's kind of one thing that's glaringly missing from this story, and that is that where are these irreducible representations? How many are there? How do you build them? So we've reduced the study of representations to smaller things, these irreps, but I haven't actually told you how to build them, or how many there are, or what they look like, or anything about these things. We know they exist, right? We know they exist. So today we're going to deal with this. We're not going to only count the number or how many distinct irreducible representations there are. We're going to relate them to something intrinsic to the group, and we're going to show how to build them. Like how would you actually write them down as matrices? So these are the goals for today. And in order to do that, we're going to use these class functions, which I introduced in the previous lecture. Those are the symmetric observables. The observables that are invariant under actions of the group by conjugation. A class function, just to remind you, is a function from the group to complex numbers such that if you do something, if you conjugate by elements of the group, then you get the same thing again. And for certain types of symmetry operations, in particular the ones we kind of care about in quantum mechanics, these would correspond to symmetric observables, ones that don't care about the symmetry. Now, in the last lecture, I finished with proposition about class functions I'll rewrite it in a highly compressed, summarized form here so that we can have it on the board. So that because there's a very important construction that we introduced in this proposition. Namely, we take the average of all the matrices doing the symmetry and weight it by this class function. That's the proposition right there. Oops, times by the identity. This is, I mean, you can do this, right? This thing here, it could be interpreted as a way to build symmetric observables in quantum mechanics. So this thing itself will be invariant under the action of the group from left and right. That's what we proved in the proposition when we proved the proposition last time. So this is a way to build kind of like angular momentum operators for general group symmetries. I won't pursue that today, but it's something that you should bear in mind. And if this representation, I should have written H here. So if H is an irreducible representation, then there aren't that many symmetric observables you can write down. In fact, the only symmetric observable you can write down is the identity. And there's this coefficient of proportionality here with this inner product. Okay, that's where we were last time. And now we're going to use a couple of simple facts, and we're going to immediately be able to count the number of irreducible representations that a group has. Like at the moment, I would say it's completely unclear how many irreducible representations a group has, right? If I wrote down a group, if I write down the group I chose last time was Z3, right? Or Zn, like how many irreducible representations does this group have? Well, we worked it out, right? We had to do a little bit of this sort of number theory tricks, and we worked out that it had exactly n irreducible representations. But what if I write down another group? Like, would those number theory tricks work? Would they tell us how many irreducible representations there are? It's not clear, right? There's at least some detective work you have to do per group. But now I'm going to teach you a way to avoid all that detective work and just write down the irreducible representation, the labels, or label the irreducible representation. You'll actually be able to count the exact number based on just properties of the group itself. So I'm going to introduce a vector space. I'll call it calligraphic C. So we just take the linear span of all the class functions. If you have one class function and another, and you take the linear combination, you get another one. So let's take the linear vector space of class functions on the group. And here comes the amazing result. This vector space has some dimension, right? So the dimension of the space of all class functions is DC, some dimension, I don't know what it is yet. But it turns out that the dimension of this space is exactly equal to the number of irreducible characters. Now this is a very surprising fact.
Is
Yep.
this an algebraic basis or indeed an orthonormal basis?
It's an orthonormal basis.
Orthonormal system in
In Hilbert space, yeah. We have an inner product on the space of all functions on our group, remember? I introduced it in a previous lecture, this inner product. And so, oh, there's no star with respect to that one, sorry. This vector space here with this inner product. Okay, we already know okay, it's still maybe not obvious that we've just found a way to count how many irreps we have, but we're one step closer. So these characters, what do we know? Well, they form an orthonormal basis with respect to that inner product. That's something we've proved before. So that part is done, right? So orthonormal, the word basis, right? We've proved that they form an orthonormal system. That was a theorem 2 lectures ago or last lecture. All that remains to show is that there's nothing missing out, that we've got a full basis here. Okay, so we want to show that every one of these characters the characters themselves are class functions. Remember, that was fairly easy to conclude. So all characters are class functions. Now we're trying to do the converse. Are all class functions linear combinations of characters? Well, for that to be for there to be something wrong, for there to be a counterexample, you'd have to have a class function that's orthogonal to all of these characters. Otherwise, it would be a linear combination already. So we're looking for something that's orthogonal and a class function to all characters. Okay, but this would mean that it's orthogonal to all the characters. Okay, so far so nothing. And what we're going to do is combine this comment here with the proposition above. So what we're going to do is we're going to start by testing this statement out and the consequences of this statement out on an irrep wj. So we'll write this out next, what I mean by this. So we assume we have one irrep, we just choose one of these irreducible representations, we don't know which one it is, but we just choose one. We build this operator rho f, sum the class function over this operator like this, but we know that the character, that f is orthogonal to all these things here. So if we work out and then proposition above implies that rho f is equal to, and there's a number, but this tells us immediately that rho f is 0. So if we have a class function that's orthogonal to the span of all these characters, and we have an irreducible representation, and we build this operator, then it's 0 immediately. Further, for any representation, so this is true now for all. This statement here is true for all irreducible representations. We just chose one, but since it didn't matter which one we chose, we'd always get this result. We actually now know that for any representation, rho f, remember these decompose into a direct sum of irreducible representations, tensor some stuff, which I can write as m. Right, I had this decomposition in the last lecture. But these things, these are all 0 now, thanks to this statement there. Yep.
We did that assumption that this is 0 because we put character equal trace row t, right?
Yes.
But if we wouldn't put trace row t, then what?
You mean here character trace row t?
Yes.
Yeah, in fact this should be chi j because we chose...
Can we choose other character?
Not quite. Yes, because every character is a linear combination of these characters here. I could have put any character in here, yeah. Effectively I'm doing exactly that right now, yeah. Yeah, so you're thinking one step ahead, I think, yeah. Yeah, so we've just learned that any representation, this operator rho f featuring in the proposition up here is actually 0, because it has to be 0 on the irreducibles. The irreducible representation is a direct sum of, any other representation is a direct sum of irreducible representations, and these things are all zeros. It's always 0. So there's one particular representation we like. So for the regular representation, rho f r, let's say, let's call it rho f r. Right, we've got the regular representation. We build this thing according to proposition above. It has to be 0, right, because of the stuff we've learned already. So in particular for the regular representation, rho f is also 0. So what, you might say, right? Well, now remember how the regular representation is built? You pick vectors. There's an orthonormal basis for each t in the group. And there's also a vector for the identity element. That's how the regular representation acts. But now we're going to put this, I'll put the row r up there to make clear it's a regular representation. Now we're going to take this, and we're going to put those two facts together. And then we're going to see something very interesting. So let's go back to the top of the proof here. We supposed that there was a class function that wasn't a linear combination of these irreducible characters, that there was something beyond. And then we worked out that if there was something beyond the span of this, then firstly, any rho f operator would be 0 if the irreducible representation was 0. Therefore, any rho f type operator is 0, no matter what the representation. And therefore, let's just choose the regular representation. So this thing equals 0, right, by the above assumptions. And then we just act this on an element inside the regular representation, in particular the one labeled by the identity element of the group. And then we see that if we act this operator, which is 0, right, on this identity vector here, then we get that this linear combination here is 0. But now we have learned something, because this is an orthonormal basis And the only way a linear combination of orthonormal vectors can be 0 is if the coefficients are each separately 0, right? Because whatever this is, right, this is some vector, we'll call it psi, and I can start taking inner products with psi, and psi equals 0, and that gives me f of s. So I've just learned that f of s is 0 for all elements of the group. So if we had a weird class function orthogonal to all the characters, the only way that could be is if the class function itself was completely 0 on every single element of the group. So f is a linear combination of the irreducible characters. And now we can put all of this together. We've now leveraged information, and this is the point that we've been building up to. We've converted information about irreducible characters into information about class functions. And class functions are defined only on groups. They don't, once you've written down the group and the group multiplication table, you can work out the space of all class functions. We'll do that in a second. And if you know the space of all class functions and the space of all characters, and you learn that they're the same dimension, you know that class functions and characters are really each other in disguise, in linear combinations. So that's how we're going to get to the final result that will tell us exactly how many irreducible representations there are, what they look like, and everything like this. So before I reveal that result, I want to tell you a bit more about conjugacy classes and class functions. So let's forget representation theory for the moment and just think about groups. Remember, a group is a set of things and there may be multiplication rules and inverse rules, and it's just a bunch of things, right? And I'm going to draw a group as here's my Venn diagram of a group. Now, there's a thing called, there's many equivalence relations you can build on groups. You know, where you say two things are the same in the group. And there's one particular equivalence relation which is very, very useful in the context of class functions. We say that t is equivalent to t prime if there exists some element of the group G such that t prime equals st s inverse. So this is an equivalence relation. You can check that it's reflexive, transitive, and whatever the third one is called, I forget. So it's definitely an equivalence relation symmetric. Symmetric is the third property. And what does it mean when you have an equivalence relation? It means you can glom together all the things that are equivalent inside the group. So here we go. Here's the element, the identity element in the group. How many things are equivalent to the identity element under this equivalence relation? Are there other elements that are equivalent to the identity element? Right? Because the only thing that's equal to the identity element conjugated by something in the group is the identity element. So the identity element sits by itself in its own conjugacy class, right? But certain elements, other elements, non-zero elements, non-identity elements, there may be things they're conjugate to that they get equivalent to, right? And so you can sort of break the group up into these classes of all the elements that are equivalent, right? There's another T prime in here, ST S inverse. There's a U prime in here, SU S inverse, and so on. The group breaks up into classes of equivalent elements, but the identity is in its own class, right? And these classes of equivalent elements are called conjugacy classes. And what's that got to do with class functions? Well, there's a very important property about class functions. They're constant on conjugacy classes. They give a unique function from conjugacy classes to the complex numbers. Now, one thing I want to stress here is that the number of conjugacy classes I don't know what we're going to call that number. I'll call it K. The number of conjugacy classes for a group is something you can work out just from the group multiplication table, right? You can write down all the elements of the group and you can multiply them all together, and then you can work out which ones are equivalent to which. You don't need to know about representations, vector space, or anything like that. The number of conjugacy classes for your group is something determined by the group itself, and it's something you can write a computer program to solve in, I don't know what, order of group cubed time or something, right? And so it should come as a surprise when I say that the number of irreducible representations of a group is equal to the number of conjugacy classes. I mean, okay, I've been building up to it by now. It should become less of a surprise when I say something like this, because you've seen all the bits and pieces that have been built up. But now we come to the main result. So this is super, right? What we discovered is a way to count the number of irreducible representations of a group without having to do this number theoretic detective work that we did in the previous lecture. All we have to do is work out how many conjugacy classes the group has. And that's something that I claim you can do with a computer and 3 for loops, right? Yeah, that should do it, 3 for loops. You can probably even think up cleverer ways to do it. And so this is a algorithm that tells you the number of irreps. based on just the group itself. The group knows how many irreducible representations it has. So this is something we can now prove, and the proof is not even that long. So let's give these things names. That's C1, this is CT, and so on, right? We're going to give these conjugacy classes names. Just call it big C and then the conjugacy class. And then the element that generates the conjugacy class. So I've already practically given you the proof. It's in this line above here. Class functions f, a constant on conjugacy classes. So how many, or what's the dimension of the space of class functions? Well, to each conjugacy class, there's a corresponding number, right, which is the value that function takes on that conjugacy class. I'm going to write I'll write T here, right? T1. Oops. So the space of all functions on conjugacy classes has a dimension. It's the number of degrees of freedom that you have. And how many degrees of freedom? We have this many complex numbers that you are allowed to distribute. So we've actually just counted the dimension of the space of class functions. So the dimension of the class functions is equal to k, the number of conjugacy classes. Just from this fact that that's the degrees of freedom that we have to define a class function. But by the previous theorem, we now know that that's equal to the number of irreducible reps. And we're done. It's so simple. So let's do an example. This is how we should have done the example last time, right? Z3Z. Pretty simple group. Let's work out how many irreducible representations this group should have. So let's write out its group multiplication table. Okay, that's the group multiplication table for Z3. Remember, it's addition modulo 3. So let's count the number of conjugacy classes for this group. So suppose we have T inside our group. Let's work out all the things that are conjugate to T inside this group. So T prime is conjugate to T. Now remember, our group rule is addition modulo 3, so I could write that as S bar plus T plus S bar inverse. So circle plus means addition mod 3. But addition commutes modulo 3 or not, right? So that's S plus S inverse. The inverse of S mod 3 is whatever, 2 plus S bar or something. And so S plus inverse is 0, so it's actually T bar. So the only things that are conjugate to T is T bar itself, right? So every element is its own conjugacy class in this group. So here's the group, there's 3 elements. 0 sits in its own conjugacy class, 1 sits in its own, and 2 sits in its own conjugacy class. And that tells us that there are 3 conjugacy classes. K equals 3. Therefore, there are 3 irreducible representations of this group. There, no? That was pretty easy. In fact, for all abelian groups, this argument here didn't really need to depend on the addition modulo 3 and all that stuff. This is actually true for all abelian groups. Right? So every element in an abelian group sits in its own conjugacy class, so that K, the number of conjugacy classes, is the order of the group. And if you put that together with what you know from the last lecture, you now know that every irreducible representation of an abelian group is one-dimensional. Maybe next lecture, if I have time, I'll tell you about the connection between the Fourier transform and this fact here. So the Fourier transform, I'll say it in words now so that you can sort of, I can spoiler it, right? You can see that there's something very interesting about abelian groups. If you have a class function on the group, then that's just a function on the group, right? Class functions are functions when you have an abelian group, because all these conjugacy classes, they have one element in them. So in fact, the number of conjugacy classes is the number of elements of the group, and any class function is therefore just a function on the group. It's nothing the word class is no longer special. But class functions are a linear combination of characters. So every function in your group can be written as a linear combination of these things called characters. It's a basis change from the basis where you have the kind of position basis to another basis, the basis given to you by the orthonormal characters. And these orthonormal characters for an abelian group, they're very special. They have this special e to the I pi factor kind of thing. Turns out that that basis change is the Fourier transform. So if you have the real numbers or any abelian group like this, the basis change from writing your function on the group as in terms of this position basis to this space of characters, that's just the Fourier transform. It is the Fourier transform. So this is a very sophisticated way to look at the Fourier transform. It in fact tells you how to generalize the Fourier transform to beyond the real numbers to all groups. Anything that has an abelian group structure, you now know the Fourier transform for it. It even works for non-abelian groups. This is a gigantic generalization of the words Fourier transform. Super useful in physics. We do it all the time. Why do we do it all the time? Because we want to write invariant things in invariant bases, right? That's why we choose to do the Fourier transform, because things that are covariant with respect to translations are better in frequency space. We know that. Why is it better in frequency space? Because we have class functions, and class functions don't care about position. So let's go to frequency space. That's a better place to do our work, because we want to work in terms of the basis that's invariant, and that's the Fourier transform. So this is the beauty of this result here. So I hope I get to say more about it, but you know, maybe I'll just leave that here as a kind of placeholder, so that maybe one day in the future, when you start thinking about more general symmetries or looking at systems which are symmetric beyond just translations, and you're like, oh, I really want a nice basis, then you remember that there's this thing called the Fourier transform, and that you can apply it to any group, not just the real numbers. So that's something really cool. Like that's like what we've learned. This is the beginning. This is the kind of the end of the course now. Like, you know, we're starting to harvest all the rewards of building up these definitions and ideas, and we're going to plant little seeds. Like the little seed that is the world of Fourier transforms over arbitrary groups is a huge, gigantic field of research, super useful in understanding signals theories in all kinds of contexts. And once you get into the world of Fourier transforms and groups, you quickly come to special functions. So this is another deep rabbit hole that we also won't be able to go down. But it turns out there's a very deep connection between special functions like the Bessel function, Legendre function, so and so and so on, and symmetry representations in groups. And you should start to begin to sense this, right? Because the characters of the real numbers, they turn out to be these e to the ikx's. The characters of any nice linear group, like the cyclic group or the real numbers, this is these Fourier phase factors. And that's an orthonormal basis. Great, whatever. But now, you start to think a little bit more. You think, well, okay, if those characters were interesting and gave us an interesting basis of functions, what if I changed the group to something really different? Not just the cyclic group anymore, not just the real numbers, but I change it to some, you know, funky group, some Lie group or something like that. Then I'm going to get characters as well. Those characters are there, and they're going to form an orthonormal basis. And those functions, they're going to play the same role that the Fourier factors played in the Fourier transform. And then you're like, well, I know about other transforms. I know about the Hankel transform, I know about the Bessel transform, and so on. And you start to wonder, maybe they can be interpreted as the characters on some group. And the answer is yes. So all of these transforms where you write one function in terms of a linear combination of other functions, these transforms, all Hilbert transform, all of these transforms can be interpreted as changing your basis on some group. And that turns out to be very, very powerful in the right, when it's used properly, right? You can just sort of dive into it and get really, and have lots of fun with the genre functions and so on. And that's good, you know, Chebyshev polynomials, you can do that just for its own sake. But when your physical system tells you what the symmetries are, it tells you what the characters are, and it tells you what transform you should be using. All right, so before ending this topic, I want to write down one consequence of all of this that's quite useful. It's got lots of information in this proposition that can be useful in particular examples. And so we'll try and harvest all this information as best we can. Yeah, this is little c. Oopsies. All right, what is this proposition telling us? It's telling us some quadratic functions on characters. But the proof will be more interesting than the statements in the proposition. You'll understand the proof better, I think, than the proposition. I would translate this into a completeness relation, just so that you have a sense of what quantum mechanically is being said here. So I'd call this like this. That the sum of these things, right? That's an orthonormal basis, so we know that that's got to be equal to the identity in quantum notation. And if I apply that to an element of the group, right? So this is some operator, right? Call this whatever, P. And if I do this, then I should get the delta function, right? In the regular representation. This is how I translate these two statements, right? This thing here is whatever, right? Some quadratic outer product of these class functions. This is the class functions evaluated in this position basis. This is the completeness relation. So all we're picking up here is that the completeness relation is that this operator here is effectively expressing the completeness relation. So I've written equal to identity, but it's not actually equal to the identity. There's a proportionality factor that you have to get right. But otherwise, it's a completeness relation. Good, then let's go ahead and prove this statement. Okay, so we're going to introduce an indicator function. Oops. So if S is in the same conjugacy class as T, we make f of S 1 and 0 otherwise. Let's introduce this. It's a class function. As it's a class function, we can write it as a linear combination of characters, right? And what are these lambdas? Well, they're just the inner products. And I'll leave that as an exercise to work out that constant factor here. This proportionality factor. If you write out this inner product here, you insert the definition of this inner product between the character and the class function, and you sum over all the elements, then you'll see that you get the number of class elements in the conjugacy class of S times by the character. Oh no, the star's gone. And you'll see this G factor comes from the fact that this inner product here has a G factor, and you want to cancel that out. So that's a little exercise for you. And then we just write out that function in terms of the basis with these coefficients here. Okay, let's do a slightly more meaty example, a non-abelian group. We're not going to muck around with abelian groups anymore. Let's do something non-trivial. So instead of doing Z3, we're going to look at the group of permutations on 3 letters. So this group is S3, the symmetric group on 3 things. That's a group we've met before earlier in advanced quantum theory. It's not a big group. It's only got 6 elements, but it is non-abelian. So sometimes doing one thing then the other is not the same as the other way around. So let's work out, let's first list all the elements. There's 6 elements, so I'm going to draw them first of all. Right? If you know my permutation representation where I just draw how each element gets mapped under the group to its image. We've got 3 letters, let's call them A, B, and C. So the first permutation on the letters A, B, and C is do nothing. And then we can cross the first 2, A, B, C. We can cross the second 2. And we can cross the first and the third and leave the middle one alone. So there's 3 transpositions. And then we've got 2 more elements, and they are the cycles. So there's this one, and its inverse. So I've listed all 6 elements now of the symmetric group. And the symmetric group on 3 things. Let's name these things. Let's call this 1, right? The identity element we'll call 1. Makes some sense, doesn't it? Let's call this one T. And let's call this one C. You'll see why I'm focusing on just these 3 elements in a second. Now, it's often convenient to generate a group from a fewer number of elements just by multiplying them. Sometimes you can generate the whole group with just one element by multiplying with itself. That's the case for the cyclic group. For the symmetric group, we can't generate the whole group with just 1 and T, but we can generate the whole group, when we can't generate the group with just 1 and C, but we can generate the group when we have 1, T, and C together. And so I'll show you how to do that. So let's note some algebraic relations. Firstly, doing T twice is just the same as nothing. And if I did everything correctly, then if you do C 3 times, you get the identity. If I cycle once, cycle twice, cycle 3 times, I get the identity again. And if I did everything correctly and chose the right 3 elements, then if I do TC, I should get C squared T. I bet I didn't do it right. Let's see. Firstly, it should be commented that this is C squared, right? And is T then C the same as TC squared? I'll do a little side computation here. T what have I done wrong? Yeah, okay. So this is Okay, I'm going to make, I know if I continue trying to check this, I'm going to make a mistake for the next 5 minutes. So the only error I could have made in this entire computation is getting C and C squared wrong. So it could be that I meant to have chosen this one to be C and that one to be C squared. So it's a homework for you to choose the correct one. Check that. You've got to choose C to be correct so that this relation is fulfilled.
I think it works.
It works? Great.
I think so.
I guessed correctly. Thanks, you did the homework. That was really quick. Good. So why is this interesting? Because this tells us what the conjugacy classes are. So C inverse is C squared. So T is in its own little conjugacy class with 1. T is in its own, it's in a conjugacy class. It turns out that, in fact, the 3 T's are in their own conjugacy class. So we'll call this T prime and this T prime prime. And the C's are in their own conjugacy class. Whoops, no, that. Forget what I just said. But what I did say is correct, right? So the conjugacy class built from just the identity, that one's an easy one, right? That always just has the identity in it. There is the conjugacy class of T, and how will I explain this? It contains all the primes and all the transpositions. And there's the conjugacy class of little c, which contains c and c squared. Now, how could I be so confident in writing these down? Well, in the symmetric group, if you have some element in the symmetric group pi, and you take a conjugate element, so you take something else in the symmetric group, let's say sigma inverse, then what does this do? It just relabels, the sigma and the sigma inverse relabels the targets. So it's like, it just swaps around A, B, and C, but on both sides of the permutation. So sigma inverse relabels A, B, C, then you do the permutation, and then you do sigma, and then that relabels back the elements. So according to this, a transposition stays a transposition under conjugation. No matter what you do before and after, it's always going to be a transposition. It'll always obey this relation, t squared is 1. And a cycle is going to stay a cycle. If you're cycling between a bunch of elements and I relabel the elements, it's still a cycle. It might be a different cycle, but it's still a cycle. It's still going to obey the equation c cubed equals 1. That's how I could be so confident as to just say these are the 3 conjugacy classes. Of course, if you go to bigger symmetric groups, it gets more complicated, but we are not going to do that. So we know that there's 3 characters, there's 3 irreducible representations. There's an irreducible representation corresponding to this conjugacy class. There's an irreducible representation for this conjugacy class. And there's another one, theta. We can already understand these characters. This has a name, actually. This is the signature of the permutation, right? This one's the easy one. This is the trivial one. So chi of 1 is just 1 for every element in the group. There's another one called the signature of the permutation, which we've met many a time before, SGN. And this is a character, and it obeys an equation, namely the sign of the transposition squared is equal to 1, so it's plus or minus 1 depending on the number of transpositions. So the solution when it's minus 1 on a transposition. And there's another one, right? This other character. We don't know much about that. But for the symmetric group, you always get two characters. One is the trivial one, and one is the signature of the permutation, which features in the fermions. And there's the other one. And so we can start to work out how big this representation is, and other little trickery things, right? So let's remember a result about the regular representation. The regular representation has dimension equal to the order of the group, which is 6. And now remember this, so the dimension of the theta representation is n. We do not know what n is at this current point. We know that this is a dimension 1. We know this is dimension 1, because these are abelian groups, but we do not know what the irreducible representation corresponding to this third irrep here is. So the regular representation has dimension 6. Now remember this result, that the dimension of the regular representation, 6, is equal to the dimensions of each of the irreps squared, summed up. So that's the same as 1 plus 1 plus n squared. So that tells us already that n is 2. The missing irreducible representation of the symmetric group is no longer a one-dimensional representation, it's actually two-dimensional. And now we're going to exploit all these little things that we've learned in the past weeks to work out what this character theta actually is. We know there's a irrep of dimension 2, and its character of this irrep is theta. But theta is a character, we don't know very much about it yet. But we do know this character here, and we do know this character here. And we do know something else, right? The character of the regular representation, whatever, pi, is a sum of all the irrep of the characters multiplied by their multiplicity, right? Remember this result? So that's chi1, which comes with multiplicity m1, plus the signature representation, which comes with multiplicity chi mt, which is 1, right? Because it's dimension 1, plus 2 times theta, whatever theta is. And there's something neat about the regular representation. We know that the character of the regular representation is like 1 or 0. So this equals 6 if pi is the identity and 0 otherwise. So let's work this information out. We're going to summarize all the information we now know in a table. So what do we know about the trivial representation? What values does it take on the group? So the trivial representation always takes I could have written every element of the group out on the top here, but there's no point in doing that, right? So it makes far more sense to write out all the elements in the conjugacy classes, because chi will never take a value different on these elements here. So I'm going to specify the function chi on the whole group, but I'm going to do so by just writing out its values on the conjugacy classes. You can work out its actual value on a given element. So what values does it take? Well, that was easy, right? It's always 1. Now we have the signature of a permutation. On the trivial conjugacy class is definitely 1. If you have one transposition, which is what this conjugacy class has, that's all the elements with one transposition, then the sign of that permutation is -1. And if you have a cycle, then the sign of that is actually 1 again, right? Because you have 2 transpositions to make a cycle. And now our mystery character, the one we don't know what it's like. Well, we have a relation, right? We know that m times chi1, which is 1 times 1, plus m2 times chi t, which is 1 times 1, plus 2 times the mystery character had better equal 6. So that is that. And 1 times this plus 1 times this plus this had better equal 0. It's the only way that could satisfy this relation up here. And 1 times this plus 1 times this plus 2 times this had better equal 0. So it better be -1. So this is called a character table. This thing plays an extraordinarily central role in representation theory. This is the thing, with the character table you have all the information at your disposal, as we'll see in the last lecture, to build all the representations of your group. There's no missing information here. This tells you what the value, tells you all the characters. It has to be square, right? Because there are as many characters as there are conjugacy classes. And the value of each character on any element of the group you can work out by just going along this line and finding out which conjugacy class the group element lives in. And then, yeah, that's it, right? And the columns add up to 6 or whatever the order of the group, or 0. And each row is orthogonal to each other row, thanks to all these orthogonality relations. Yep.
But is there always enough information? What if we have more than one mystery character?
I mean, okay, is there always enough information? Suppose someone's given you the completed character table. Then there's no missing information. You can get everything you want. Of course, if you don't have the character table, how would you build it up? Well, there are mystery characters and you have to do some detective work. It's not completely for free, but it's almost determined by these relations here. This relation for the regular representation, the orthogonality relations, and this dimension result here can give you a large amount of the information you need to build up a character table. But the good news is the character tables are all written down for all groups. So someone's done this hard work. You can just look in a book or even on the internet. These days you can just Google the character table for your favorite group. Once you have the character table, then you can actually build up the irreducible representations themselves. You can actually write down the matrices that do these things. That's the topic for the next lecture, but I can already write out the construction in these last couple of minutes because it's just the averaging trick. So I'll write it down. Suppose you want to build the matrices that do this irreducible representation here. How would you get them? Well, you would write out the following operator. So let's assume that our representation here, rho t, let's assume it contains the irreducible representation you want. Then this thing here is a projection onto that unitary representation. So let's imagine doing this now in practice for this group here. So we have to find a representation that has this weird theta rep inside it. And there's one that we always have for free. It's the regular representation. So we start with our regular representation here. That's 6 by 6 matrices, right? And we build this operator. So I suppose I can do this in 5 minutes. So P theta, I reckon I could fit it in here. Because number theta divided by g. Now I've got to sum, and I've got to take the character, right? The character corresponding to the representation I want. Well, it's this chi theta. So I've got to take 2 times the identity, which is a 6 by 6 identity. I've got to sum with it 0 times by all the transpositions of the regular representation. Well, that's easy, 0, 0. And then I'm going to subtract from that the matrix representations for the cyclic, the 2 cycles in this conjugacy class here. And they look like this. How do they look? How do they look? Oh, man. Yeah, okay, I admit I don't know how they look. So there's, I think it's something like this. Poop. Yeah, okay. I thought I could do this real quick, but I can't because I have to have the group multiplication table for S3 and I don't know that in my head. But they're going to be two further unitary permutations like this. And you build this thing here and you add them up and you'll get a projection operator. And that projection operator will project onto a subspace and that subspace will furnish you that missing representation. And in our case, it'll be 2 copies of this representation because in the regular representation, we have 2 copies of this theta rep. But that's something we'll do next time. Yeah, I thought I could do this tricky quick, but I couldn't. So just, for later. All right, so that's the goal for the next lecture. We're going to project onto sub-representations and hence build them all once we have the character table. And that will be the end. We will have reached the end of the course. So, but that's it for today. Thank you very much.